In grade 10, we learned several aspects with regards to the Cartesian plane and trigonometry. And what we do in grade 11 is we put it all together. And in grade 11, we learn the bulk of trig that will form our main knowledge for our second paper. So what we see here is we have a quadrant and we have certain angles that are shown in these quadrants, and we will label these quadrants according to the angles of the x-axis, starting with a 0 degree, a 90 degree, and we are working in a clockwise, in an anti-clockwise direction, and 270 degrees down there and back to 360 degrees. Now, when we just worked with basic constructions and triangles, things like that, we realized that we were able to work within a 90-degree triangle. This 90-degree triangle allowed us to perform two operations within it. These operations were known as Pythagoras, or we would work with our ratios, our trigonometric ratios. Let me just draw these nicely here, and then another one here. Right, so after we learned that we are able to do Pythagoras in a 90-degree triangle, we also learned that 90-degree triangles allow us to perform our trigonometric ratios. Now, these trigonometric ratios exist because of the 90-degree triangle. Further on in grade 11 this year, we will go into more depth where we will work with normal triangles where we do not have 90 degrees, but that's when we learn the sine rule, the cos rule, and later on our area rule. And these are reserved for techniques applied in triangles that do not have a 90 degree. So going back to our revision of grade 10 work, our grade 10 work basically showed us, introduced the concept of theta, beta, alpha, our angles. And in this triangle, I have ratios according to sine of theta, cos of theta, and tan of theta. My two-dimensional shapes are flat. I have the opposite side, I have the adjacent side to theta, it all pertains to theta, and then I have my all-important hypotenuse opposite my 90 degree. Now, together with the theory of sine of theta being opposite over hypot, cos of theta being adjacent over hypot, tan of theta being opposite over adjacent, we translated that and we went and drew that triangle in the Cartesian plane. Now, within the Cartesian plane, we then learned to deal with this 90-degree triangle of the x-axis, and we labeled it according to our y-coordinate that we know exists here, our x-coordinate that we know exists here, and a radius r that we calculated there. Now, according to Pythagoras, r squared is in fact equal to x squared plus y squared. That is why we would always consider these aspects to be true in the Cartesian plane, are always being a positive length, because it is like your circle in our Cartesian plane. So when I have a circle in my Cartesian plane, I can draw an axis within that circle, and according to the coordinates that lie on the edge of that circle, I will have the radius equal. So doesn't matter what angle I extend off my 0 degrees, it would always have the same radius. So radius, 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 radius. But what we find now is that we have an angle here, or here, or here, and that angle, however big it is, can be reduced to exist in this quadrant, in which we work with acute angles. Now that is an x and a y coordinate. That is an x and a y coordinate. Therefore, we see we've got various x, y coordinates lying on the circumference of the circle, and those x, y coordinates exist in such fashion that whatever the angle is, it would be in relation to these coordinates. And again, whatever this angle is right here would be in relation to these coordinates. So each section that I've indicated here exists within its own relationship of x to y and r. So, sorry about that. So what we have now is we are using our knowledge of sine theta, cos theta, tan theta within the two-dimensional triangle, and we apply it in our cost diagram. We apply it in the Cartesian plane. So our Cartesian plane exists of the original x and y plane. We work off the 0 degree line, which is indicated by our x-axis, and we learn to work with a positive angle, which is anti-clockwise, and a negative angle, which is clockwise. Now we go one step further, and we ask ourselves, according to these ratios that we so often use, where would I find these ratios to be positive, negative? So positive or negative is determined by whether my x coordinates are positive or negative, or my y coordinates. Now that is where cast comes in. Cast works with the fourth quadrant starting with C, and it means that cos is the only positive ratio in the fourth quadrant. The first quadrant contains positive ratios for all ratios. The second quadrant, only sine is positive. The third quadrant, only tan. So now, when I work with this, I am going to take something, for example, sine of 190 degrees. And I'm going to ask myself, but this is a very big angle. It's an obtuse angle. And I don't want to work with an obtuse angle. I want to work with an acute angle. And we have this idea in trig that we actually already know this from having studied trig graphs, that there are various angles that will give me the same y coordinate. So if we do that, we'll see our typical sine graph looks something like this. But if I take my constant here and I see at every red dot, I will have the same y coordinate, but at that position it would indicate a different x coordinate, which means a different angle. So I can actually take this very big angle and reduce it to equal this very acute angle. Same for this one, back to the acute, same for that one, back to the acute, because they all end up having the same overall answer. So what does that mean for my cast diagram? we use the cast diagram to perform reduction. We first try and express our angles. So I'm going to draw a new cast because this one contains the diagram as well. And I'm going to use a new cast diagram where I just insert my angles. And this diagram will eventually become your platform for all your theory. It will be your go-to for every exam you write here on forward. Without it, you cannot do it. So you first insert cast, and then you label your angles accordingly. This is theta. This quadrant is where theta exists. This quadrant is where it's 180 minus theta. Here's our 180. As soon as I'm in this quadrant, I'm at 180 plus theta. And in this quadrant, I work with a negative theta. As I indicated here, we're going anti-clockwise. It's positive theta. But when we go clockwise, it's a negative theta. That only exists right here in this quadrant where cos is positive. Or another way is saying I've got 360 degrees here minus theta. That's the other way of stating it. So all I do now is I go and look at sine of 190 degrees. It's obtuse, but sine of 190 degrees is very close to 180 plus something. So I first ask myself, where is 180 plus something? So I'm going to make it look relatively the same. And I'm going to equate the 190 to 180 plus 10. Then I'm going to find my quadrant and see, okay, but sine in this quadrant, which is what is positive and negative here, only tan is positive here. So sine is negative in this quadrant, which means my answer is going to be a negative sine answer. And I reduce 190 degrees straight to 10 degrees. Because the rule states that sine of 180 plus theta is reduced to, according to this quadrant, it's reduced to negative sine of theta. And you can do that for every single ratio. I can give you cos of 230 degrees. Firstly, let me find where 230 degrees would exist. And once again, it's in this quadrant right here. So let me express 230 in terms of 180 plus. So you want to go to your 180 as it is the closest. So you're either adding or you're subtracting, or as soon as you have passed 270, you will work with 360 minus. So rule of thumb is to always know where your 0 degree is, 90 degree, 180, 270. But to be very sensitive for this one, please, we do not encourage that you work with 90 and 270 plus or minus when it comes to tan, which we actually know from graph work already, the asymptotes of tan. That is why the tan graph looks the way it looks, because it both lies on the 90 and 270 degree axes. It's your y-axis. That's why tan is undefined there. But when we view our angles with respect to 180 minus, 180 plus, we don't often work with 270 minus and 270 plus. So let's rather work on 180 plus, and I find myself saying, what do I add to 180 to get 230? That's 50 degrees. Which means, according to theory, cos of 180 degrees plus theta, I find my quadrant. 180 plus puts me in this quadrant. I ask myself, is cos positive or negative? Cos is negative here because only tan, and I reduce it straight to a negative cos of theta, which should then give me the answer here, negative cos of 50. Now, what does this mean? It means that there is a part of trig where we will assess your ability to perform the technique called reduction. And reduction is when we get typical questions that look like these. And we will ask you to reduce, to simplify these questions using your trigonometric ratios and your understanding of reduction. We just get one for you here. And the instruction is usually just to simplify. Now, as with any other technique in maths, once we've learned to simplify, we apply the techniques according to the work that we are working with. And this would be a lovely example where we fuse our understanding of ratios, our understanding of positive, negative values, and we then see we are able to reduce these very huge angles to smaller acute angles and therefore simplify this expression. What I start with is, once again, I'm going to tackle my angle as it's given. That is my number one clue. And then I'm going to assess whether it is positive or negative. So you always need your cast diagram right there next to you. So tan of 360 degrees minus theta. I firstly go to 360 minus theta. It places me in the fourth quadrant. I ask myself, is tan positive or negative there? Tan is negative there. And I reduce 360 to minus tan of theta. Then my next one is cos 180 plus theta. I go to 180 plus theta. I ask myself, is cos positive or negative there? Cos is negative. And I reduce it to negative cos of theta. Being mindful that I have a multiplication there and that I have a separation of terms here in the denominator. Now I look at my denominator very closely and I see cos of 360 minus, and I'm back at the fourth quadrant, and cos is in fact positive there. I reduce it straight to cos theta. I keep the negative that separates my term. And now I go to cos 180 plus theta. Now cos 180 plus theta is again situated here. Therefore, I indicate it within a bracket because it turns into a negative cos of theta. Now, let's just quickly go back to what was given. If you had the urge to perform something like this, you're on the wrong track and you need to stop yourself right now, because this is not allowed because of that negative separating a term. So our rules apply as it did with simplifying for x and in algebraic fractions. We have to first consider how many terms are we working with, and are we allowed to cross cancel? Division turns into multiplication different times, that stays the same, but treat signs with care. So now what I can do is I can simplify this by looking at the negative times the negative at the top, which then gives me positive. So I can just simplify that and say tan of theta times cos of theta minus times a minus is a plus. Now at the bottom here, I have cos of theta plus, because of this right here, cos of theta, and it is good to remember, treat sine of theta or cos of theta or tan of theta as you would have treated x. It's the same idea here. If you had 5x, it's the same as saying 5 sine theta. If you had 5x squared, it's the same as saying 5 sine squared theta. On your calculator, the square does not appear here. If you were to substitute a value into the calculator opens its bracket. You insert the angle and it closes it, then you need to square it. But the overall result is to always remember the original ratio as such is still squared. My overall result is still equal. I've kept the integrity of what I've started with. Therefore, the square is applied. So don't think the rules are different. The rules are still the same, simplifying, applying those techniques. So I can simplify my denominator by saying I've got 2 cos theta, right? And now I'm actually in a position where I may go ahead and cancel something, only because I have 1 term. This is so important. I did some algebra with the grade 8s, and that concept of just going around cancelling, we must not perform it over plus and minus signs. So this results then in tan of theta divided by 2. Now, there is just one more aspect that we do add to our theory, and it's the aspects that develop from using our x, y, and r. And it's very much what I took from this triangle. If I were to express sine of theta in this triangle, called, for example, now with theta here, there's my y, there's my x, there's my r, then in this triangle, this green one right here, if I were to express sine of theta, I would say sine of theta is opposite y over r. But in that very same triangle, if I were to express cos of theta, I would say cos of theta is equal to x over r. And what I find is that if I were to answer the question, simplify sine squared theta plus cos squared theta, I would have to take what ratio I've developed for sine squared and what ratio I've developed for cos squared, and I would have to replace them with regards to their lengths, and I would treat them very carefully as I treat fractions, and I would add the knowledge of Pythagoras to this and use that in order to substitute what I find in my denominator. So now y squared over r squared plus x squared over r squared allows me to work with this expression x squared plus y squared over r squared. And that's where this connection comes in from Pythagoras, that r squared is in fact equal to x squared plus y squared. Therefore, we are replacing r squared over r squared, and my answer is 1. And that is where we often see this identity being used. We used to prove it a lot in grade 10, but now we are going to use it as an identity, and we assume that theoretically all grade 11s should know that sine squared theta plus cos squared theta is equal to 1. Together with this very important part of theory comes one more part of the theory, a list of aspects which is considered theory for us, and that would be the understanding that tan of theta is equal to sine of theta divided by cos. of theta. Now, how can I make that statement? Let me investigate what is sine of theta, and I'm going to go back to my original one. It's y over r. What is cos of theta? It's x over r. Therefore, what is y over r divided by, because that's what I have here, sine is y over r divided by cos, which is x over r, allows me to perform my tip and times, and I see that I may cancel the r, and what I'm left with is y over x. And let's check what is y over x in my original triangle. In my original triangle, y and x would be tan of theta. Tan of theta is opposite over adjacent. So that's where all this theory falls together into a section reduction. Within reduction, we use certain identities to simplify things, and we use conversion from obtuse and reflexive angles into acute angles, and we treat it with care when it comes to fractions and simplifying.